Hi everyone, welcome back. In this video we will learn about alkenes and alkynes. Now alkanes are saturated hydrocarbons, which means that they are loaded to capacity with hydrogens. And up to this point in previous videos, all we've worked with are alkanes. And so for example, butane, which is 4 carbons long, is saturated with hydrogens. And remember, we kept adding hydrogens so that carbon had 4 bonds. So C4 and then H10. So we're going to refer to N as the number of carbons. So in this case here, N is equal to 4. And so if we take 2 times 4 plus 2 is equal to 10. Therefore, non-cyclic alkanes, so what I mean by non-cyclic, it's not a ring structure. Non-cyclic alkanes have the formula of CnH2n plus 2. Alkenes are hydrocarbons that contain at least 1 double bond, and alkynes contain at least 1 triple bond. So if you hear the word alkene, I want you to think double bond. If you hear the word alkyne, I want you to think of triple bond. Now these compounds, alkenes and alkynes, are missing hydrogens and therefore referred to as unsaturated. Non-cyclic alkenes have the formula CnH2n. So you see here, we are missing some hydrogens that we originally had in the alkane formula. So let's look at an example here. This is butene. And I want you to pause the video and fill in the hydrogens and then determine the molecular formula for butene. All right, welcome back. Let's check your work. There should be 2 hydrogens here. 1 here because it already has 3 bonds. 2 here and then 3 here. And the formula is C4H8. Now there's a term associated with losing those 2 hydrogens. It's called a degree of unsaturation. So 1 degree of unsaturation is equal to 2 missing hydrogens. Non-cyclic alkynes have the formula CnH2n minus 2. So we're missing even more hydrogens here. Now if we looked at an example of butane, I just want to make a note here. Remember that triple bonds are sp hybridized, which means they have a what type of bond angle? 180 degrees. Excellent. So you never want to draw a triple bond in a zigzag fashion like this because you're not honoring the bond angle here. It should be 180 linear. So let me teach you how to count this. Sometimes students miss a carbon when they're counting across a triple bond. So here we have 1, 2. They usually miss the second carbon. 3, 4. So be sure to not break that bond angle there if you have a triple bond as drawn here. Now, what is the molecular formula for butane? C4, and then if we draw in the hydrogens, there's 1 at the end. No hydrogens on carbon 2 because it already has 4 bonds. We have 2 on carbon 3 and 3 on carbon 4. So a total, we have C4H6, which fits the formula CnH2 and minus 2, because 2 times 4 is 8, minus 2 is 6. Right? So you can always, if you are just given the molecular formula without this structure, you can determine if you have possibly a triple bond, a double bond, or if you just have a saturated alkane. So triple bonds have 2 degrees of unsaturation. In order to form a triple bond, you need to lose 4 hydrogens. So now whenever you read about saturated versus unsaturated fats, now you understand that something that is unsaturated has a double or triple bonds in it, and something that is saturated has, its full capacity of hydrogens on the carbon chain. All right, so let's go ahead and talk about nomenclature of alkenes and alkynes. Before diving into this section here, I urge you to practice problems from the previous video, learning the nomenclature of alkanes, and practicing more naming of alkanes on your own, because we're going to use those rules and then build upon them for alkenes and alkynes. So let's go ahead and get started. The parent chain for an alkene or alkyne is the longest continuous chain that contains the double or triple bond. So it must contain it, right? It's still the longest chain, but it has to be the longest chain that contains the double or triple bond. And the way we name the parent, we don't have the ANE ending anymore. We use ENE for alkenes, and we use YNE, ine, for alkynes. Now, students often ask me, well, could you have a molecule with both a double and triple bond? And yes, you can, and those would be ene-ines. For my course, we would not have those molecules on an assessment. However, if you do go on to take more organic chemistry, you'll see them in that class. So we number the parent chain to give the double or triple bond the lowest number. So when we just had alkanes, remember back to the previous video, we numbered the parent chain to give the substituents the lowest number. Well, double and triple bonds have priority over substituents. So that's why it's critical for you when you're asked to name an organic compound to identify like what's present there. Is there a double bond? Is there a triple bond? Is there some other functional group? And in my course here, we're not going to dive into naming alcohols and carboxylic acids and esters and so on. You would do that in an organic chemistry class. But it's really important you have a strong foundation in naming alkanes, and then you just just build upon that when you're introduced to a new functional group. But it's important to be organized and to have practice so that you do the rules correctly and in the right order. All right, so the last step would be to follow the rest of the rules in naming as you would name an alkane. So let's go ahead and get started. Now we're looking at this example here. What is the longest carbon chain that you can find that contains the double bond? And you can go ahead, and I challenge you, stop the video, try to do it on your own, following the rules that I've provided you in your experience with naming alkanes, and see if you can do it on your own, and then revisit to check your work with me. All right, the longest carbon chain I see is this one here. I like to use my highlighter. There we go. And so when we name this one, originally, I always start with the alkane name. So it's 6 carbons long, so that would have been hexane. But we drop the A and E, and we replace it with what? The E and E. Fantastic. All right, now it's really important that we note the location of the double bond. So we have to number such that the double bond gets the lowest number. We don't even look at the substituents just yet. We just look at the double bond. In this case, this molecule is symmetrical. So you can number from right to top or from top to right. It doesn't really matter here. So 1, 2, 3, 4, 5, 6. Now the way we indicate where the double bond starts is we write hex 3-ene. Remember, we always separate numbers and letters with hyphens. And we put the number directly in front of the ending. We always, with double or triple bonds, use the lowest number, so where that double bond begins. So at position 3 in this case, you would not write hex 4-ene. Then that would indicate the double bond would be here instead. So always use the smallest number where the double bond starts, and also for the triple bond as well. Now, I think it was in the 90s that IUPAC, it was the committee who comes up with these rules for systematically naming organic compounds. Originally, this number was out in the front, but they changed the rule to put the number in front of the ending, which I personally like better because there are times where you have 2 endings. So for example, if you had a double bond and an alcohol, it's an ene-ol, and so it's a lot easier to see that the number in front of the suffix. So if you have a 3-ene, 1-ol, then you know, okay, the alcohol is at position 1, and then the double bond's at position 3. Like, it just makes it easier to decipher. So just something to make note of. The reason why I'm telling you this is that you may find in resources that you find online that people are still using the old naming system. But I do prefer the new naming system, since that's the one that we are currently using by IUPAC's rules. All right, so we definitely have hex 3-ene. Now we need to identify the substituents. What are these 2 substituents called? Fantastic. They're methyl groups, and since we have 2 of them, what prefix do you use? Excellent. This is a dimethyl. What positions are the dimethyl in? 3, 4. All right, and now we glue everything together, all one word. This is a 3, 4 dimethyl hex 3-ene. There you go. All right, let's do the next one. What is the longest carbon chain that you can find that contains the triple bond? Hopefully you found this one here. All right. And so how many carbons long is that? And we have to number to give the triple bond the lowest number. So we do have to number from right to left. So this is 1, 2, 3, 4, and 5. So technically that would have been pentane if it was just an alkane. But we drop the A and E and replace it with Y and E. So this is now pentine. But what position does a triple bond start? Position 1. Excellent. So pent 1 ine. All right. And then what substituents do we have? What's this group called? It's the fork in the road. It's an isopropyl. Very good. So we have an isopropyl 3. And what other group do you have? This is a methyl group. Excellent. So 4-methyl. Now we have to glue everything together, all one word. And remember, substituents in alphabetical order. Now something I want to make note of is this very common mistake. Students often think iso is a prefix, but it's not. Isopropyl is the common name for this particular alkyl group, and so the I is included in the alphabetical rule. So given that information, which substituent goes first? Yes, the isopropyl goes before the methyl. So let's write that down, all one word. So we have 3-isopropyl, 4-methyl, pent 1 ine. Fantastic. All right. I think sometimes students, I remember with this example before, I'm going to draw this structure again because there's another carbon chain that's 5 carbons long that includes the triple bond. So I just wanted to highlight that for you. So this one here, 1, 2, 3, 4, 5. However, if that's the one you found, you're also correct. That's why I wanted to say that. Because 2, 3, 4, 5. This is still 3-isopropyl, 4-methyl, pent 1 ine. Okay, so sometimes that happens too, where you have 2 carbon chains of the same length, and they would give you the same answer, and that's okay. Whereas what we saw in the previous video, you had 2 carbon chains of the same length, but one gave more branching than the other. If that's the case, yes, you want the more branches. However, in this case, they're both the same. They gave the same name. All right. Now, something really neat about alkenes is that they have geometric isomers. And the major difference between a single bond and a double bond, and if you have models available, then make, for example, and I'll show you 1,2-dichloroethane versus 1,2-dichloroethene, and you'll see that with an alkane, you can rotate around the single bond. You have this free degree of rotation. But with alkenes, you're kind of locked in due to that double bond, due to that pi bond, right? So let's write that down real quick. That we have the degree of rotation in a single bond, whereas a double bond we don't. So let me draw my example here. Okay, so this is 1,2-dichloroethane. Now, just a side note here, if you have a halogen, so remember the halogens are fluorine, chlorine, bromine, and iodine. If they're substituents, then we take the first syllable chlor and then we drop the I-N-E and replace it with O. So it turns out fluorine turns to fluoro, then we have chloro, bromo, and iodo. Just as a side note here, and let me write those down for you. I'll just write them at the bottom. So you have chloro, bromo, fluoro, and iodo. We do see halogens quite a bit in organic molecules, so it's important we know how to name them as substituents. All right, so this is 1,2-dichloroethane. It's 2 carbons long here, and it has 2 hydrogens here. And what you would find is if you were to build this molecule here, you could rotate between carbon 1 and 2. You just keep rotating that model. And these carbons here have what type of hybridization based on valence bond theory? sp3. They're both sp3 hybridized carbons. Now, if you were to build a model that has a double bond, looks very similar, but we lose a degree of saturation. And so originally we had 2 hydrogens on each carbon here. But in this case, we have 1 hydrogen on each carbon. And what is the hybridization of those carbon atoms? They are both sp2, which means how many unhybridized p orbitals do they each have? They have 1, because remember there are 3 p orbitals in a p subshell. 2 are being taken up by these hybrid orbitals, so you have 1 left over. And I'll just draw that as like that dumbbell shape. And that's where these electrons are located. We discussed this in the previous videos. If you need a review over that, please do so. So alkenes have pi bonding. And remember that pi bonding occurs in p orbitals, those unhybridized dumbbell p orbitals, and it is sideways overlap. And you can think of this sideways overlap as just locking everything in place to prevent rotation from happening. And so because of this, we need to designate if we have a geometric isomer. In this case, we do. And what you'll notice is the chlorines are on the same side of the double bond. And if something is on the same side, we call it cis. So cis is on the same side. If you're looking at 2 groups, opposite of those 2 hydrogens there. So the name of the structure I've shown here is actually cis 1,2-dichloro, because there's 2 chlorines, eth, 2 carbons, 1 ene. This particular structure here has a geometric isomer. Another way you could have drawn this molecule here is to have the chlorines on the opposite side. And if you do have model kits, you can't rotate the cis structure to look like this. You actually have to break the bonds, right? And so that's why they're isomers. They're geometric isomers of one another. And so the chlorines in this case here are on the opposite side, and we refer to that as trans. So when the groups are on opposite side, they are trans. And so the name of this structure that I've shown here is trans 1,2-dichloro eth 1 ene. just something to make note of here. Anytime we have what's called stereochemistry, like we have here, we write that out in the front of the name. You will also notice that the name of the molecule is the same, and that's why they're isomers of one another, but they have different geometry. And so this is different than constitutional isomers. Remember, constitutional isomers have the same molecular formula, but different atom-to-atom attachment, right? However, with geometric isomers, they have the same molecular formula, and the atoms are attached the same. They just have different geometry. And so that's why these are called geometric isomers. This only happens we're only going to discuss this happening with double bonds, with alkenes. If you go on to take organic chemistry, you're going to learn about other types of what we call stereoisomers in that course. But for right now, we're only focusing on alkenes. Alkynes do not have geometric isomers, and neither do alkanes. So alkenes only, but I want to identify what makes something have a geometric isomer. Not all alkenes do, is basically what I'm saying. So for example, if you had an alkene that has two of the same groups attached on the same side, so I'm just showing an example here. So you see here, these are the same groups. This structure cannot have because no matter how you rotate this particular example here or build it, there's not going to be a cis or a trans. And that's because two of the groups attached to the same carbon are the same. And that goes for example, terminal alkenes, where you have two hydrogens on the same side, on the same carbon. Those don't have geometric isomers. There's no cis or trans. And so these groups need to be different from one another, like a hydrogen and a methyl group, as well as on this carbon too. Now, if, for example, I showed you here that, we have a chlorine and a hydrogen and we have the same group on this side, but because this chlorine's on a different carbon, then we can have geometric isomers. So I just want to make that clear, that if you have the same group on the carbon on one side of the alkene, then no geometric isomers will occur, okay? So to kind of sum that up from valence bond theory, the pi bond in an alkene restricts bond rotation and remember we have free bond rotation here in alkanes, but not with these double bonds and these alkenes. And because of that restriction of bond rotation, we have the potential, remember not all alkenes have geometric isomers, we have the potential for geometric isomers, and these are referred to as stereoisomers. So there's a whole field of stereochemistry, and that these are isomers that have the same molecular formula, same atom-to-atom attachment, but different 3D structure. And if you, like I said, if you go on to take more organic chemistry, then you'll dive in deeper into stereoisomers. All right, thank you for watching and see you next time.